Today's lesson is on section 4.7, graph linear functions. First thing we're going to talk about today, though, is just how we can work with functions and function notation. We've seen, first of all, this form very often lately. Slope-intercept form, y equals mx plus b. I'm going to show you function notation because you're going to notice something that they look very similar. Function notation, a linear of a linear function, looks like f of x equals mx plus b. So these parts right here, the right sides of our equation, are both really the same exact thing. The only difference between slope-intercept form and function notations is on the left side of the equation, they just look a little different. Slope-intercept form, we have y equals mx plus b. Function notation, we have f of x equals mx plus b. So why do they use this particular notation? Often when they're talking about functions, we're usually talking about a function applying to some kind of real-world situation. And in a real-world situation, often, we can plug some kind of number in and get an answer out for what we're looking for. And so function notation is just kind of a handy way to do that. As you get into higher levels of algebra, they'll get something in function notation and they'll name it as such, and then they can work with it in programs or just easier communication. When we talk about the difference between function notation, or first I'll say how we read this. Function notation, this part here in the front, where it's f and then in parentheses with an x in the middle, this is read f of x. And what that means is it's a function where x is the independent variable. So I should see x in parentheses here in the middle, and also x on the other side of the equation. That's our independent variable. That's the variable that we're going to be plugging numbers in for and evaluating and getting answers out with. So f of x means this is a function where x is the independent variable. There may also be other forms, or other names for functions like g of x or h of x. That's how functions are named. That first letter is the name of the function, but it's saying that it's a function of, and then whatever variable is in the middle here of the parentheses. So that means that's the independent variable we're talking about. That's the variable we're going to plug numbers into and get answers from. One other similar thing I want to point out about function notation and slope-intercept form is that when we work with them, they often do the very same things. We can plug numbers in, get answers out from them, and not much really changes for how we use them. It's just a different, function notation is just a different way to write an equation that we will see on MCAs and in higher level algebra. So it's something we need to understand when we see it, what we're looking for, what we're trying to do with it. But it's just another way to write similar problems like we've had. Look here, I've got what's the difference between the graph of an equation and the graph of a function. What is the difference between the two of these? We'll look at the equation and the function. They both look exactly the same, except this one's an equation in slope-intercept form, y equals 3x plus 1. Here's now, as we're learning, function notation, f of x equals 3x minus 1. So they both look exactly the same on the right side of the equation. If I'm going to graph the blue one up here, y equals 3x minus 1, I could use slope-intercept form. I could say the slope is 3, the y-intercept is negative 1. And the slope, again, if it's like 3, it's like 3 over 1. That'll remind me where to go when I get to the grid. My y-intercept is negative 1. So that means I'm going to go down 1 on the y-axis and put a point. My slope is 3. So I go up 3 over 1, up 3 over 1, up 3 over 1. I got to find more points on this line. There's what the graph of that equation, the blue equation, slope-intercept form would be like. So what's the difference between that and function notation, or this function here? How would I graph this? Well, I guess as I'm trying to point out to you, it's really the same exact thing. The slope is 3. The y-intercept would be negative 1. Again, I can think of the slope as 3 over 1. Along my y-axis, I'm going to go down 1 for the y-intercept. And my slope's going to tell me to go up 3 over 1, up 3 over 1. So there's the graph of that equation, or that function, I should say. So notice, they are the exact same thing. Function notation, very similar to the equations we've been dealing with. So when we see these, what I want us to do is not be too worried when all of a sudden I see f of x, or I see g of x, or some kind of function notation. Because just know it's the same things we've been working with. We can do the same types of things. We can evaluate, we can plug in numbers, and we can graph, just as I've shown you here. Well, in this section, one of the first things they want us to do to start getting comfortable with function notation is evaluate functions, and they have a different form for doing it. Again, it's something we've done way back since chapter 1, and probably in previous grades the students have done this. But this is just a different, with function notation, they ask for it a different way. So I just want us to get familiar with this. Some line to copy down here if you're taking notes along with me. Start here. It says, just like we did with expressions and equations, we will plug numbers into a function to evaluate it for certain values of x. So this problem right here says evaluate the function, and here's my function. F of x equals 3x minus 1, that one we were using from the first page. Evaluate that function when x equals 5. So just like we've done in the past, we dealt with way back in chapter 1, we dealt with expressions that did this. They're saying, well, figure out what the answer is, evaluate. Remember, evaluate has almost the word value right in the middle there. So find some kind of answer, find a value. That's what evaluate means. Find a value for this function when x is equal to 5. So that means I'm going to take 5, put it right in for x, and see what I get in this function. So f of x equals, well, I'm going to have 3 times, no, and I'm going to have 5 instead, minus 1. 3 times 5 is 15. 15 minus 1 gives me 14. So when I put 5 into the function, I get 14 for an answer. There's a different way they usually have you write this, though. When they talk about function notation, when they want you to plug 5 into the function, another way they might ask for it is they'll write it in this notation that I've gotten shown down here, where it says something like f of 3. So as opposed to being f of x, they're saying for this function f that we're talking about, the one we have above, they want you to put 3 in for x. Because notice, usually in the function, there's an x in there. Okay. Well, now coming back to this, it's saying, oh, put 3 instead. That's saying put 3 in where the x is in the function and see what you get for an answer. That's all they're asking us to do in this problem. So that if you see something like f of f, or sorry, f of 3, or f of 7, or f of negative 2, what it's asking you to do is just like this problem above. It's telling you put that number in for x and see what you get for an answer. So let's take a look at that and see if you can get the right answers along with me here. This first one, what it wants to do is we're going to work with that same function up there, f of x, 3x minus 1. This is saying put 3 into that function. So what would happen? Well, then that means that I'd have 3 times 3, and then I'd subtract 1. So 3 times 3 gives me 9, minus 1 would give me 8. So here's how you'd really write that answer. In that function f, f of 3 equals 8. Because that means in the function f, in this function called f, that's the name of it, if I put 3 in for x, I get 8 out for the answer. Move on to the next one here. F of 7. That means in this function, I'm going to put 7 in for x and see what you get. So that means I would take 3 times 7 and then subtract 1 from it. 3 times 7 would be 21, minus 1 would give me 20. So f of 7 equals 20. That means in that function f above, 3x minus 1, in that function, when I put 7 in, I get 20 out for an answer. Again, is this part, especially this evaluating part, is this anything different than what we've done in the past? No, it's not. We've always evaluated functions or plugged numbers in for x and found an answer. This is just function notation, though. The way they ask for us to do it is by saying find f of 2, find f of 3, f of 7. That's what we have to do for, that's how they ask in function notation for us to do the same things we've been doing for a while. We just need to get comfortable with that form. This last one, f of negative 2. That means I'm going to take 3 times negative 2 and then subtract 1. 3 times negative 2 gives me negative 6. Minus 1 gives me negative 7. So f of negative 2 equals negative 7. That's how in function notation they ask us to plug a value in for x. So just kind of re-emphasizing what we were doing on that previous page. Here's another function. Again, functions can have different names. This one is g of x. For the function g of x equals negative 4x minus 10. Again, this is just any letter could be in the front there, but that's just the name of the function. They're calling it g. For the function g of x, again, there's an x here. That means there needs to be an x in the actual equation. That's our independent variable. That's the number we're going to plug. That's the variable we're going to plug numbers in for and find answers. So if it says g of x, that means the function's named g. and x is the variable that's you're gonna find over here on the right side of the problem. And what do you know? There it is, negative 4x minus 10. So what they might ask for then, as it does below here, it says for g of x for that function, find g of negative 1. Well, that means negative 1 is in the place of x right here. It used to be g of x. Now it's g of negative 1. That's just telling me put negative 1 in where x is in the function. So I'm going to take negative 1 and plug it right in there. So negative 4 times negative 1 minus 10. Again, this should look familiar to students. This is something you did way back in chapter 1 and probably in 7th grade and 6th grade and grades before, evaluating expressions like this. But now this is just the way function notation asks us to do that. Negative 4 times negative 1 gives me 4. Minus 10 gives me negative 6. So in this case, f of, I can leave this up here. But if I'm going to write the answer, I was going to say f of, in this case it's g, my new function g of negative 1 equals negative 6. When I plug in negative 1, I get negative 6 for the answer. That's what that's saying. Okay. This next one here, g of negative 5. Negative 4 times negative 5 minus 10. Negative 4 times negative 5 gives me 20. Minus 10 gives me 10. So again, if I'm going to represent this answer, I'm going to say g of negative 5 equals 10. That's how I say that in the function g, the name for that function g. When I plugged in negative 5, I got 10 out for the answer. This last one here, g of 3. That means in this function, I'm going to put 3 in for x. See what I get. Negative 4 times 3 gives me negative 12. Minus 10, that gives me negative 22. So if I'm going to say that I plugged in 3 and got negative 22 out for the answer in this function, I'm going to say g of 3 equals negative 22. One more thing they may ask us to do with function notation that, again, will be like something we've done in the past. We just need to know what they're asking for. Is they also might have us find the value of x that would give us a certain answer for the function. So as I have there written in red, again, something else I want you to write in your notes, is we can also plug numbers in for f of x and solve for what x should be. Look at this question here, and you'll see how it's asking for something a little different than the previous page. For this function, f of x equals 2x minus 10, find the value of x. We're looking for what x could be so that the function will equal 6. I want to know what number can I plug in for x that'll end up equaling 6 for an answer once I multiply by 2 and minus 10. This is something different than what the previous page was asking. As I'll show students here in class, and as some of them will start to figure out, well, the way I can do that is I'm just going to set something up here like a little equation. We're going to say, well, 2x minus 10, there's the function. I want to know when this equals 6. So I just make this little two-step equation. And we solved two-step equations way back in chapter 2. And you've probably been doing that, again, in 7th grade, maybe even 6th grade. You've been solving equations just like this. How do I solve this equation and find out what x has got to be? Well, I try to get x by itself, so I draw my line. It says minus 10, so I add 10. Things we learned way back in chapter 3 here. Now I just have 2x on the left side still. On the other side, I have 16. I'm just solving this little two-step equation to find out what would x have to be so I would get an answer of 6 in the function. In this case, I'm finding out that x equals 8. If I want to make sure that's the answer, I could just plug 8 back in there and make sure that that's what I get for an answer when I evaluate. 2 times 8 gives me 16 minus 10. Yep, that would be 6, which is what I'm supposed to get. Very good. So this problem is a little different than the previous pages. They're saying what could the value of x be so that we get an answer of 6. Well, what I tell students to do is just make a little equation just like we've done in the past. Set that function equal to what you're trying to get, and then solve it there and find out what x would have to be. So looking at these two problems, just like we did in the previous page there, it says for the function g of x, and there it is, 4x minus 4, what I'm trying to find is the value of x so that g of x equals 28. So again, I'm trying to figure out what could this be. So when I'm done, this equals 28 after I multiply that number by 4 and then subtract 4. So again, what I tell students in class here is I say make a little equation. Well, if I want to know when that function equals 28, just set the function equal to 28. 4x minus 4 equals 28. I'm going to draw my line. I could add 4 to both sides. 4x equals 32. Divide both sides by 4. X equals 8. Again, if you want to check and make sure it works, take 8, plug it back in here. 4 times 8 gives me 32. Minus 4, yep, that gives me 28. So that does work out. So that should be my answer. X equals 8. That's the last one. P of x equals negative 2x plus 9. Find the value of this function, find the value of x, I should say. Find the value of x for this function so that P of x equals 4. I want to know what do I have to plug in here. What could I plug in there so that this equals 4? So again, my big hint to students is just set that function equal to 4. Negative 2x plus 9 equals 4. Solve it like a little two-step equation, just like we've done in the past, and you should find your answer. If I subtract 9 from both sides, I get negative 2x equals negative 5. Divide both sides by negative 2, and I get 5 over 2. Or again, in this case, you can, because it's not like a slope, you could just write 2.5 is what that ends up equaling. So good. So knowing how to use function notation, again, as you look at what we did here in this lesson, is anything new or anything we haven't done in the past? No. These problems here, we're just solving a two-step problem, some kind of two-step equation. Some of the ones before, we just evaluate an expression. But we just need to know what is function notation. In certain ways they ask for us to do things using function notation. As long as we can understand that, I'm pretty sure we can get to the answers because it's just like things we've been doing for a long time.